Hello, my name is Tommy. Do you want to see my collection of random numbers? This is the title of a talk that was given by me and my friend Knut at an IT developers conference. It's a crash course in computational statistics, and it might be interesting to you if you're a programmer or you know how to program and you're interested in or you know a little bit about statistics. If you know a lot about statistics and computation, then it might not be the thing for you. If you like it and if you want to look at the figures, it's all on GitHub, so you can go to this URL and you can see how the code was run and how every figure was created. We'll look at a lot of examples and just touch in on many small interesting things. Let's go to the agenda. First, I'm going to give you a little refresher about statistical concepts. Then I'm going to introduce Monte Carlo assimilation, resampling techniques, stochastic search for solving optimization problems, and finally Bayesian statistics. And we'll see that with some programming and having the ability to generate random numbers, we can solve a lot of fun problems really easily, and it gives us a way to do statistics and optimization without having to do a lot of theory. It might not always produce the best result. It's not statistically as rigorous as some other approaches, but these techniques are really powerful because they're easy to program and you can solve a lot of problems with them in a decent way and have a lot of fun. So hopefully that's interesting. Let's just jump into it. So this is the definition of a probability. I won't say much about this. It's a number between 0 and 1 representing an event that always happens, extremely likely, and 0 being an event that never happens. And for instance, if you toss a coin, the probability of getting heads is a half, so 0.5. So it represents belief, or it represents how many things something happens if you do it many times over. You can get really philosophical about this, but we won't. Here's a data set. This is the height of 50 people. It's from a book called Handbook of Small Data Sets. And this is the height in centimeters of 50 people. So what can we do about this? Well, we can make a histogram. And the histogram is kind of an empirical probability density function. It tells us that the probability of observing someone that's around 165, 170, 175 in that range is quite high, but the probability of observing someone who's 190 is probably not that high. Here it's 0 if you trust this to be exact, if you trust this histogram to represent every human, but it's just a sample of 50 people. If you're willing to make what we call a distributional assumption, if you're willing to assume that this comes from a theoretical probability distribution, you can fit a distribution to this data. For instance, the normal distribution. And that's often assumed with heights as an introductory example, that the height of humans is normally distributed. So you take a normal distribution and you take your data, you figure out the mean value and the standard deviation, measures of centrality and spread respectively, and with that you can draw a normal distribution. And if you trust the normal, then there's a probability of observing someone who's 190 or a bit higher, but it seems like most people are between 140 and 195 or something like that. So we have the empirical approach, just use the histogram, and we have the more theoretical approach where we assume that it's normally distributed and we fit a normal. We can also fit a cumulative histogram. And with a cumulative histogram, we can find what's called empirical percentiles. And these are the numbers such that a proportion of people is lower than or equal to that number. So for instance, P10, that's the height such that 90% of people are taller than this height. So 90%, that's 45 of these people are higher than 157. P50 is also called the median, and that's the height, 169 here, such as half the people are shorter and half the people are taller. And P90 is on the right side. It's the height such that 90% of people are shorter than this height. And you can figure it out by looking at the cumulative histogram and starting from the left here. So for instance, P50, if you go on the y-axis and you imagine drawing a line till you hit the histogram and then you go down, you'll find that where it intersects, that's the number that gives you the P50. Here too, we can look at the cumulative normal, and we see here that it fits the data quite well. There's a lot of bins here, and when you draw histograms, not the cumulative ones, but the normal ones, it's always a bit hard to say how many bins to use, because it can make the data look very different. And it's good to just use a routine, usually some kind of algorithm, to automatically select the number of bins, so you don't have to think about it too much. Now that we have our normal distribution fit, we can use the normal distribution to find percentiles. In that case, it's exactly the same. You start on the left, for instance, for P50, and you go to the right, and when you hit the orange line, you go down, and that's your P50, assuming the normal distribution. Whereas if you go till you hit the empirical cumulative histogram, that's your empirical percentiles. There's only a few probability distributions worth knowing about if you're getting started. There are hundreds, but most of them are for more fancy modeling. I recommend reading a bit up on this if you're interested, but for our purposes, we just need a few. The normal distribution, it has quite thin tails, and it's usually appropriate for things like height. Lognormal, it's skewed and it's always positive. Might be more suited for things like people's income, because you have some that have very high incomes compared to others. Or it might be the popularity of songs, for instance, might be lognormal. So lognormal, and when you have things that are a bit more skewed, especially you have some Pareto principle, you actually have something called the Pareto distribution as well, but it's the idea that there are some outliers and you want to capture those. The uniform distribution, maybe the simplest distribution there is. It's just equally likely, typically between 0 and 1. And then the triangular distribution, also very intuitive, why it's called triangular, and you can shift it around a little bit. It doesn't have to be symmetric. That's all we need to get started. So here's log-normal distribution fit to some drilling times. And these are oil well drilling times. And we can see from our distribution some numbers. We have the mean, which is the center of gravity of this probability density distribution. So if you were to use your finger and balance it, you would put it at the red line. You have the median. That's the number such that half the probability density is to the left and the other half is to the right. And then you have the mode, which is the most likely value. And of course, in normal and uniform distributions, all of these three numbers coincide, but they don't when we don't have symmetric distributions. So in general, they don't coincide. Let's talk about calculations with distributions. We want to sum two numbers. So assume you're an IT developer or something like that. You have two tasks. You estimate them both to take between 1 and 2 days. And you wonder what's the probability of the sum. So when will I complete both of my tasks? So the first thing to notice, that's maybe not intuitive if you never thought about this before, is that the sum of x and y has a different shape than z. So two uniform distributions, when you add them together, the result is no longer uniform. The result is triangular. And even though the mean value actually turns out to be 3 here, so 1 plus 1.5, 1.5, add them together, you get 3. If you try to add percentiles, it doesn't add up, because the percentile of x, the p10 of x and y is 1.1, but if you add them together, you get 2.2, but actually the percentile, the p10 of z is 2.45, so it doesn't add up. So it's not easy to compute with probability distributions. There are some computational rules for things like the mean and the variance, and you probably learned these in school, but we're just going to ignore all of that because we'll soon see that there's an easier way to do all of this stuff. To summarize, to handle uncertainty in a consistent way, it's important to have some base knowledge about probabilities, probability density functions, and cumulative density functions. It's also nice to know that the histogram is kind of like an empirical distribution. You can also fit theoretical or parameterized distributions to data, and there are hundreds of these, but you only need to know a handful to get started. The 4 most common ones is uniform, triangular, normal, and lognormal. Some important properties of datasets and of distributions: the mean, the p10, p50, that's the same as the median, and the p90. Of course, you have other percentiles, like you could look at the p25 or the p75 or even the p5 or things like that. Then theoretical rules for manipulating probabilities and probability distributions are really difficult. You almost never want to do the math all the way through. It's really hard, and as programmers, we don't want to do that stuff if we can avoid it. So I'm going to teach you some nice tricks to get around it and still get good results and be able to reason about probabilities. So if you have a probability density function, you can use that to draw numbers. You can sample from it. And if you sample enough numbers, it might look something like this. You see the uniform, it's all equally likely, but for the normal, there's more values around 0. And if you take those samples and you create a histogram, you should recover the original theoretical distribution that you started with. So we can sample distributions on computers, and unlike back in the day when sampling was really expensive, you can sample tens of thousands of these numbers very quickly. That gives us an idea for how to solve the problem of adding probability densities. So you take x and y, and let's assume that we didn't know the theoretical distribution for z, that it's supposed to be triangular. We could just take x and y, sample from it, and then add them together and look at the histogram. And we can use those samples and that histogram to make inferences about p10, the mean, and p90. And we get pretty close. The mean was 3, and here it's 3.008. The p10 was 2.45. That's a true theoretical answer. We get 2.42. That's close enough in many real-world applications. And we didn't even draw that many samples here. If we wanted more precise results, we would just draw more samples and spend a bit more compute on the problem, and we would get it more and more correct the more samples we draw. Let's look at another example of Monte Carlo simulation. Say you have a cannonball, or you can imagine kicking a football. The distance it travels is a function of 2 things: the angle theta and the initial velocity v0. And you can program that. If you took some introductory physics, you might remember there being some equations. You go to Wikipedia, you find those, program it in Python. It looks like this. But what if you have some uncertainty in your inputs, your v0 and your theta? Well, you can just sample inputs and then run the function over and over and over again. Here I assume a 15% relative error in the angle and a 1% relative error in the velocity, and I just throw it all through my function, which is shown at the bottom here. So this is a very nonlinear function. It has a cosine, it has a sine, velocity squared, and trying to figure out the theoretical distribution of x would be a nightmare. But if you just sample it many times, you get a really nice probability density function shown here in orange. And you see that it's very far from normal. It has a funny shape. What kind of distribution is this? It's probably not one of the well-known ones. Maybe it's not known at all. But you don't have to do that math. You don't have to know that theory. Just sample it. Kick a lot of footballs or shoot a lot of cannonballs. Here's an example that might be more relevant in your everyday life. Assume that you have a kid and you want to save some money for him or her till he's 18. So you have a yearly deposit and you have an interest rate. And you wonder, well, if I input this much money every year and I have this this interest rate, what happens? If you're a programmer, it's quite easy to program. Here's some Python code. We deposit a yearly amount of 12 units of money, 1 unit of money per month, and we assume an interest rate of 5%. Then you might ask yourself, what about the uncertainty here? If you know you can deposit the same amount of money, the yearly variable, that's fine, but what about the interest rate? If you throw this in a mutual fund, you know that the interest rate is going to vary from year to year, so you might not want to assume that it's always 5%. If you change your function a little bit, you can sample an interest rate in every iteration, in every function call, and you can make a figure like this. And this is very, very powerful because now you can start asking probabilistic questions. Like you can look at year 18 and you can look at distribution of what kind of money you would have at year 18. Or you could slice along an amount of money and ask what's the probability that I get 200 units of money before 12 years, for instance. So if you slice it along the x or the y-axis, you can start asking questions and get probabilities out. Of course, if your input is garbage, if your interest rate is way off, you don't know anything about what it could be, and you give it crazy input, you'll get crazy output. But if you give it reasonable input, you'll get reasonable output, and this is an easy way to introduce some uncertainty and get a feeling for how uncertainty might affect your situation. In summary then, Monte Carlo simulation uses uncertainty in inputs to estimate the uncertainty in outputs of a function. It's very simple. You just draw many random realizations of x and you examine the outputs. You make plots or you look at percentiles and things like that. Given a function f, not saying it's always easy to program f, but once you have f, it requires little math and it's easy to program. You just need to generate some random numbers, feed them through, be able to make some plots and visualize the result. However, you should be aware that it can be hard to create distributions for x. For one, it's hard to know what's reasonable in some situations. If x has high dimensionality, things might be correlated and it might be hard to know what combination of parameters that are reasonable. And sometimes f is really time consuming to compute, so that might also be a problem. Now we're going to look at resampling and resampling techniques. So resampling in code, quite easy. You can do this with a numpy package. The first thing that's shown here is a permutation. That's just like shuffling a deck of cards and you just permute the order of the elements. The second one is what's often called bootstrapping or resampling, and it's resampling with replacement. So now it's like putting it back into an urn and drawing again. So the same element could come up several times. And then you can do this with probabilities or weights. So drawing some elements is more likely. And you can do that with or without replacement. And you don't have to draw the same number of elements always. You could, for instance, draw 3 elements. but the most used thing is permutations or resampling with replacement, also called bootstrapping. So very easy to do in code. How it works under the hood is roughly you generate a random number between 0 and 1, and you multiply that with the number of elements in your list, and you round it down, and that should give you a random index, and you access that index and you retrieve that number. So if you can generate random numbers between 0 and 1, uniform distribution essentially, then you can draw random indices, and then you can draw random elements. So that's how it works. You just need to be able to generate some random numbers. With some thought, you can do all of these cases. Here is a dataset with heights and pulses. It's the same dataset that we saw before, but this time it's not just heights, it's also the pulse of people. And here's the source of the dataset. It's from the Handbook of Small Datasets, that's on GitHub. And there's something called a correlation coefficient. It's a number between -1 and 1. If it's around 0, then there's no linear correlation between the variables. This is the Pearson correlation coefficient, measuring linear correlation. If it's 1, then there's a perfect linear correlation between the data. And here we get a correlation of 0.2. Okay, but what's the uncertainty in that number? How sure am I that this is the true correlation? If I were to go out and collect more data on heights and pulses, what would happen? What do I think about the true correlation in the population? Because this is just a sample. Well, one approach to figuring out the uncertainty and the correlation coefficient is to resample a dataset again and again with replacement. So I draw 50 people every time, but I allow resampling with replacement. And I get these fake datasets that look like my dataset, and for each one I compute the correlation. And you can see here that the more steep the line is, the higher the correlation number is too. Then I take all of my correlations, all of my numbers, and I plot a histogram of them. And it looks like this. So the observed correlation was just over 0.2, and here you see the resampled correlations. And what this means is that it's very unlikely that if I were to keep collecting data that the correlation would be higher than 0.6 or so. And it's equally unlikely that it's less than -0.2. And I get a feeling for the uncertainty if I were to collect more data, more than 50 data points, and I would run this analysis again, this resampling analysis, the variability would shrink and you'd get a more peaked distribution around 0.2 most likely. You can also use this to answer questions about statistical significance. You would say if your null hypothesis was no correlation and your alternative hypothesis was a positive correlation, you would say that it's statistically significant if very little falls below 0 on this figure. And with a 5% significance threshold, it would require that more than 95% of all the resampled correlation coefficients are above 0. Here 93 are below 0, so this just fails that 5% test for statistical significance. But you shouldn't be too black and white about things like this either. There's likely a correlation here, I would say, even though it does fail that test. And if you're writing papers and you didn't cheat, because a lot of people cheat, then you wouldn't be able to claim that this is statistically significant. Okay, let's keep going. Here's a fun one. This is some data from the joint bank account that me and my girlfriend have. And I was wondering, how much money do I spend in a month on groceries along with my girlfriend? And you could say, Well, you have the time series here. This is from May this year, and we could just sum it and say the answer is 8,900 Norwegian crowns. That's how much money you spend per month. But that's just how much money I spent that month. Can I say something about the other months? For instance, is it likely that I'll ever spend more than 15,000? And at first glance, it looks like I can't say anything about it because I just have 1 month of observations. But what I can do is I have the intra-month daily observations, so I can resample this data set too. It's very easy to do in Python. Here I do it 10,000 times, and I create 10,000 alternative months. These are like pseudo months or months that didn't happen. I'm just resampling my data set, creating fictitious months that never happened, but they kind of look like my month. And you can inspect this and think about it. Like, does it look like a month if you compare it to the last slide? I think it does. And again, I can compute the sum for each of these 10,000 fictitious months, and I can look at the distribution. So if I look at the P25 and the P75, it seems like most likely I'll be spending somewhere between 7,500 and 10,000, along with my girlfriend, on a typical month. Finally, let's talk about the mutual fund example. Remember that I used a normal distribution when I computed random interest rates. I could actually take this data, which is yearly returns for the SP500, one of the big stock indices, for over 140 years. And I could use this and I could resample periods of 20 years or so. So instead of assuming a distribution like normal and drawing from that, I could take this time range and use that in a Monte Carlo simulation. Then I could do it again with a different time range, and then again with a different time range. And they could overlap, but now I'm not making any distributional assumptions, and I'm using data and just resampling this time series to create fictitious, or not fictitious really, because they did happen somewhere in history, but I'm recreating these 20-year periods again and again and again, and I could use that instead of just drawing from a normal distribution like I did earlier. So that's an idea how to improve the mutual fund example a little bit. So resampling, if it's with replacement, it's often called bootstrapping. It gives an estimate of uncertainty in some parameter. That parameter could be the mean or the median or the sum, like we saw with my groceries example. It could be the uncertainty in the standard deviation or the correlation coefficient, again, which we saw, or something like the difference between two groups. So you can use this to do hypothesis testing and to find uncertainties, and you can also shift around labels and do things like that. So you can do a lot of fun things with replacement. Sometimes you have to think a little bit about how you do the resampling. Like for instance, in the time series, it might make sense to, instead of just draw random individual years, you draw consecutive periods of 20, but there's no absolutely correct answer. You can play around with it, try different things, and see what works and makes sense. However, again, it's not a perfect thing. You should be aware that sample size shouldn't be too small. And if the data is not representative, then you can run into problems. It doesn't absolve you of having little data or unrepresentative data. And distributional assumptions, like assuming a normal distribution, can be a better choice than just resampling data that you have. But sometimes it cuts the other way too, and you don't want to make a distributional assumption, and you can use resampling to get more out of your data. Next up, we're going to look at how we can use random numbers to do optimization with stochastic search. Here is a toy example, but it has real-world implications, but the real-world models are a lot more complicated. So imagine that you buy some acreage, this area and this funny shape, and you want to place 25 wind turbines on it. You have two objectives that you want to try to satisfy or try to maximize and minimize. One is that you want each wind turbine's distance to its closest neighbor to be as small as possible. So you don't want to clump all 25 together, because then you're not exploiting the wind that travels along this area very, very well. And if you're outside of the border, you want to minimize that distance, how far you're outside, because we're not really allowed to go out of the area that we bought. And of course, this is a very simplified model. It ignores wind direction, and it ignores a lot of other things like the wake effect. That's how it causes turbulence in the wake of a wind turbine and all of that stuff. So it's very simplified. But if you write an objective function and you generate 25 random points in two-dimensional space, and you just plug those points into your objective, you get a number back. That gives us an idea. We could just generate random points and we could try random things. And since we have an objective function that scores how well we do, we can compare these two. The one on the left is better, and I know why that's true here. It's because it doesn't have any wind turbines that are very far outside of the acreage. But the example on the right has one on the top left corner, and that's penalized very harshly in the objective. That's why it scores worse. So if we can generate a solution and we can evaluate it, then we can generate something, evaluate it, and then just change it up a little bit and evaluate the new thing. And if the new proposed solution is better, we keep it. If it's worse, we just do something else. So what I implemented here is first getting a random index, just a random wind turbine, and then just jittering it ever so slightly in some direction. And then I just reevaluate the objective, and if the solution is better, I keep that new proposal and keep going. If you do that many times, it looks like this, and this is quite good, I would say. I know the theoretical solution, if the area is infinite, is a hexagonal pattern, like the bees have in their beehives. So the bees know what they're doing. We're just rediscovering what bees are doing. But we have to mind the borders. So here I do the same thing with simulated annealing, and that's just adding some randomness in the start where you're allowed to accept the solution that's actually worse. And this is often a very good trick, because it allows you to be even more random and crazy in the start, but as your search progresses, you're just accepting solutions that are actually better. So this is, I don't know how long it took to run, maybe 10 seconds or so. So it's a really nice way to get started and examining optimization problems. And for some, it works really well. For others, it's a good start. Notice that it's so simple to implement, and you don't have to know a lot about your function or anything like that. So really good starting choice at the very least. Here's something that I think is a really fun example. This is based on a true story. When I started in junior high, they were taking kids from two elementary schools, and they were starting at the same junior high school. So then all of us were told to write down the names of 3 people, 3 friends we'd like to be in the same class as in the new school. And then the teacher said, we'll try to make it all so that when we assign you to your classes, your groups, you all have some friends in your group. So let's look at this a bit more mathematically. We want to place 100 pupils into 5 groups of 20, so that 1, the average pupil is as happy as possible, and 2, the least happy pupil is as happy as possible. These are two objectives, and I include them both because I wanted to mention that it's not obvious what the objective should be. For instance, if I get 3 friends and you get 0 friends in our groups, then my happiness is 3 because I get all my 3 friends. Your happiness is 0, so the average happiness is 1.5. But if we both get 1 friend, then the average happiness is 1. But the least happy pupil, that would be you're more happy with the second configuration. So depending on your politics and depending on what you think is more fair, you might want to maximize the happiness of the average pupil, or you might want to try to make the least happy pupil as happy as possible, or you might want to do something else entirely. There are many options for this. But I did these two and I just add them together, so I'm kind of trying to do a bit of both. I'm creating an objective where I get points to make the average pupil happy, and I get points if the least happy pupil is more happy. And I want to take a second to appreciate just how huge the search space is. There's 10 to the power of 18, approximately, possible solutions to this problem. First, you take 100 students and you pick 20 to form the first class. Then you take the remaining 80 students, pick 20 to form the second class, and you keep going. And then there are 5 ways to permute the labels on those 5 classes, because they're all equivalent, the permutations of the classes themselves, so you divide by that. So the search space is huge. It's a million times a million times a million. So really big search space. And to test this, if it works at all, we're going to create a problem instance with a known best solution. So each row is a pupil, each column is a pupil, and for each row, the columns indicate the other pupils, and the green dots indicate who that row students wants to have as his or her friends in class. And you see here what the solution is. The solution is these 5 classes. You can see it in the structure. So I generated a problem instance where if the algorithm is able to uncover the structure and get back to it, there is a configuration where everyone get all their friends in the same group. And the question then is, can we recover that best solution if we just start with a random assignment? So I implemented the stupidest, simplest little thing. I just get 2 random classes and then get 2 random students, and I just swap them. Then I re-evaluate the objective. So I'm not doing anything smart here at all. And if I do that, you can see in blue that the average pupil becomes more and more happy as time progresses, or the iterations progress. And at approximately iteration 10,000, the least happy pupil becomes happy too. And that's the jump at the end. And then everyone is happy, and I recovered that one solution out of 10 to the power of 18 where everyone is happy. But I just searched a tiny little fraction of the search space in practice. So it really does work. Here you can see what the solution looks like. Every row is a student, every class is a column, and the green dots indicate which class each student is assigned to. And this optimization problem was solved in 1 second, just evaluating that objective and swapping random students. So if you're doing this by hand, there's no chance you could find a good solution, I think. Or you could find a good one, but finding the best one, not likely. So stochastic search then, it's good for combinatorial problems in particular, and maybe especially if you have nonlinear or difficult objectives. The solver here is just some try, evaluate, try again loop. It doesn't have to know anything about the objective function, just has to be able to evaluate it. If you want to get a bit more fancy, you use simulated annealing, often a good idea to implement, super easy to do. You just add some randomness where you accept worse solutions initially, and then that probability, again we're using probabilities, right? The probability of accepting a worse solution decreases as the iterations progress. You need 2 things. You need a way to generate or modify a solution, So just a random assignment of pupils or swapping two pupils as a modification operator. You also need a reasonable objective to evaluate. That's the modeling part. Not always easy to know what the objective should be when you're doing this in real life, but you can always come back and try with different objectives and inspect the solutions. But in practice, when I solve problems like this for people, it's usually you go back and forth a little bit, then you add new things to the objective and you work on the objective. Usually hard to get it right on the first try. Now, it's not a perfect approach to every problem. You should be aware of some things. If the objective has a simple form, for instance, if it's linear, then you should exploit it. You can also linearize a large class of objectives, even if they aren't linear. For instance, using linear programming or mixed integer programming. There's no guarantee of an optimal solution. This is all a heuristic. When you get an answer, you don't know if it's the best solution. But if you use an optimization solver for some classes of problems, it actually reports back that this is the best solution you'll ever find. That's a very nice property to have. But you can do what I did. You can create a problem instance that has a best solution that you know what it is, and see if you can recover it with your algorithm, your approach. Typically, the performance on very constrained problems is not good because it's hard to even find a feasible solution. But this, for instance, the pupil problem, it's not very constrained. You just like creating a random assignment is really easy. So in problems like that, this type of approach using stochastic search really shines. Finally, let's talk about inverse probability or Bayesian statistics. So, on the left column, we have two deterministic problems. One is the forward evaluation or the simulation. Given some input x, determine the output f of x. And if you're a programmer, you know even this thing is not easy to solve. You have to figure out what your function f should be. You have to make sure the edge cases are taken care of. You have to write some tests probably. Maybe you have to make sure the numerics are good, and you have to make sure that every pair of inputs are handled or raised. So simulating something isn't easy, but it's the easiest out of these four. If you go down to the backward problem or the inverse problem, in the deterministic case, that would be optimization. Instead of knowing x and trying to evaluate the function, you know the output and you have the function and you want to find the input that could have produced the output. So you need everything that you needed for simulation, but you also need some kind of optimization routine to figure out what this problem means in your specific application, and finding the input that satisfies the output is typically harder. On the stochastic side of things, there's Monte Carlo. That's the forward thing. You have a distribution of your inputs and you find a distribution over your outputs. The backward problem or inverse problem is Bayesian statistics. You're given perhaps a distribution of your inputs, and you're given the results of your function, maybe with some noise, and that determines a likelihood function, and you want to use your prior along with your likelihood to figure out the probability distribution over the inputs x. So that's Bayesian statistics. It's like you have a prior over your parameters, you observe some data. How do you combine your prior belief with the data to update and get a posterior belief? We're going to look at the mutual fund again. We have a prior p of x on our parameters. We'll create that. Our parameters are two things. It's the deposit and the interest rate. We also have a likelihood, and that will be our observations here along with some measure of error. And we want to update our prior belief to get a posterior. To do this, we're going to use an algorithm called the Ensemble Smoother Multiple Data Assimilation, ESMDA. That's not a commonly used algorithm for this kind of toy example. It's used in history matching in the petroleum industry, also used in weather simulation and things like that. And it tries to find a set of parameters that are close to the observed values and close to the prior. And I'm just going to show you some plots to give you a feeling for how this works. Just know that the ensemble smoother approach is not what you would typically use. Typically, you would use something called Markov chain Monte Carlo for these kinds of problems, but I wanted to test out this algorithm. That's why I did it. So I created a distribution over interest rates and deposits, and I sampled some samples from this, and you can see the samples on the very right, and you can see the marginal histograms on the two middle plots. And each one of these points on the scatter plot corresponds to a trajectory on the left, a mutual fund realizations in the output space here. And I want to update this ensemble of inputs so that it matches the outputs more closely. So let's run the algorithm. This is an iterative algorithm, and this is what it looks like after one step, 2, 3, 4, 5, and then finally after 15 iterations it looks like this. So the ensemble on the right has the uncertainty is way lower. That's the first thing to look at or to realize. And it closely matches the observations. However, it's important to understand that the goal here is not to find the one best set of parameters that matches the observations. Then you're back to the optimization problem, the deterministic optimization problem. We want to figure out the distribution over parameters that are all likely and could have produced this setup of observations. That's a different problem. So what this represents is a balance of respecting the prior belief. It can't go crazy compared to what I believed initially, and it also wants to match the observations. Notice that there's broadly two types of solutions. Either the interest rate is low and the deposit is high, or the interest rate is high and the deposit is low. So it's capture that correlation between the two parameters. I want to just say what this could be used for. Here it's a toy example, but it's used in weather modeling and things like that, and geological models too. It could, for instance, be used to figure out the uncertainty in the interest rate. You have, 100 years of stocks, stock returns, and you wonder what's the interest rate. You could give a point estimate, but it would be nice to represent the uncertainty. So you could do that, and you could say here, given this data, it can be fairly sure that the interest rate that produces this is around 5 or 6%. You could also use it for forecasting because you have some uncertainty. So if you wanted to forecast with uncertainty, you could extrapolate further into the future. So those are two use cases. But at the end of the day, this is kind of a toy example, I have to admit. In summary, inverse probability is about finding the posterior distribution of parameters given a prior belief on parameters and a likelihood, which you can think of as like an error function on your observations. It can be used with most models that have parameters. Could, for instance, be used on a linear regression model. I think it's an excellent choice in small data problems where you don't have a lot of data, but maybe you have some experts and they have some knowledge, some prior beliefs. It's also just really nice if you want uncertainty in your parameters in a principled way. Data assimilation performs a very crude Bayesian inference, but it's the only choice when the model is expensive to evaluate, like a weather model or a geological model could take hours or even days to evaluate. And then Markov chain Monte Carlo just doesn't work because it's too slow. I hope you enjoyed this presentation. I don't want to leave you with the impression that you know all there is to know about statistics. I hope I've shown you some light-hearted ways to have fun and solve problems where you don't need to know a lot about statistics. You just know some programming, you're able to generate some random numbers, and you can kind of hack your way through it and get some really good results, especially for some types of problems. You can do amazingly well with simple techniques. But that's not all there is to it. So if you're interested in learning more, I highly recommend reading up on some statistics or some optimization, or even some popular science books where you can learn about, for instance, the flaws and fallacies of statistical thinking, just to expand your repertoire a little bit. Reading books, I think, is excellent. You get some high quality content that's hard to find online in most places, in my opinion. If you want to look at the presentation in detail or the figures, then you're welcome to do that on GitHub. If you want to run the code or if you want to play around with it, you're very welcome to do so. Thanks a lot for watching and have a nice day.